So let's go ahead and get us started here. Oh, Safa's in the house. What's up, Safa?
What's up?
You missed the chance for small talk. Like I already said, let's get started, and so that means I have to go.
Yeah, I was eating. I low-key almost forgot about the lecture. Then I was like, nah, I gotta stay committed. But here I am.
Thanks, Safa. Yeah, hey, speaking of, to everyone out there live and in the recording, I think we're like exactly halfway done with the semester. So first of all, how weird is that? That should make you feel a little jittery.
That's like weird to think about.
It is.
Honestly.
But second of all, good for us. I mean, it's good and bad. I mean, it's good in the sense that, hey, like, you know, I think we're doing well. We're going through the semester, we're learning things. That's nice. And so, you know, this is like an online semester, so it might be good to get it over with. But it also feels like, what have we done? Like I know we've done math, but just like personally, what have I done with my life? How are we halfway through this semester? If it ends, like if it ends and I've only done like double what I've done in this first half, that means I've done pretty much nothing. But anyway, I've had some fun. We're gonna have some more fun right now, and that is, what should we do first? Oh, yes, we need to move on. You might think we move on every class, but I'm saying we've done all this like divisibility stuff and evens and odds and direct proofs and all that. We're moving on today to some more interesting new stuff. We basically, not that we've done every direct proof imaginable, but we've gone far enough where it's kind of like every other proof that just uses direct proof. I think you guys pretty much have. So now it's time to learn, like, do new things that we can't do with direct proof. Can't do with direct proof. What are you talking about? We're gonna learn today. So first of all, let's just recap exactly what a direct proof is to make indirect proofs make more sense. So this chapter is all about, I guess we're on 4.7. And it's all about indirect proofs. So first off, though, what is a direct proof? So remember, direct proofs are just all the stuff we've been doing. And so the way they go is, so to prove that for all x and d, p of x and q of x, to prove that, what you really do, you say proof. You always start off with, let x be an arbitrary but particular element of D. So you always start off, you just kind of assume, you just say x is in the domain, because remember, this is a statement only about things in the domain D. So we don't care what happens when x is in the domain. So we say, let x be one of those elements in the domain, and assume that p of x is true. So we're going to let x be in the domain, assume p of x is true, and we want to show q of x is true. Because if we can show that for any arbitrary but particular, for any old x in the domain, if p of x being true implies q of x being true, then we've done it, right? Because if p of x is false, then this whole thing's vacuously true. So we only have to care about the cases where p of x is true and we're in the domain. So anyway, we're going to assume p of x, and then we need to show that x having the property p implies, or I'll say logically leads to, x having the property q. And then if we can show that for any old x in the domain, x having property p logically leads to x having property q, that means for every x in the domain, x having property p implies x having property q, so we're done. That's a direct proof. Or sometimes we might have seen it written like this. Maybe for all x in D, Q of x, where we don't have this implication of a conditional. It's just like prove Q of x is true. The weird thing is these are basically kind of the same case. It's kind of the same thing underneath. What we're going to do is we're going to say proof let x be an arbitrary / particular element of D, and then show that x having the property of being in D logically leads to x having property Q. You see that? And it goes like that. So basically the point is, the only difference here is kind of like what you assume. In this case, you assume that x is in D and P of x is true. In this case, you just assume x is in D. But it's really the same thing, because remember that for all x in D, P of x implies Q of x. What's another way we can write that? This is going back to like, universal conditionals, like section 3.2 or something like that. There's a way that we could write this and get rid of the arrow. Because remember, this is just saying that for all x in our domain D, whenever P of x is true, Q of x is true. Oh, we got chat. Oh, okay. So Benay's saying, hey, can't you just write it by, like, can't you just like write the definition of the arrow, or write like the equivalence for the arrow, which is not quite P and not Q. It's going to be not P or Q. You're thinking of the negation, Benay. So you could do that and you get rid of the arrow. What I was talking about is you could just like consider x in the set of all x and D such that P of x is true, right? This is saying for all x in the domain D, whenever you have P of x, you have Q of x. So really it's saying for all x in the domain D that satisfy P of x, meaning make P of x true, then Q of x is true. This is saying for all x in the set, actually maybe I should not use x here. Maybe I'll say U or something like that. By the way, this is saying for all x in the set of things in D that make P true, Q is true. This is doing the exact same thing. So the point is that this case and this case that I wrote up here are really just the same case. It just depends on how you want to write it. The point is you assume things, you assume x has some properties, and you just show that having those properties logically lead to having the conclusion property. Any questions on that? That's just like a recap of the direct proofs. They always go like this. And obviously the hard part is this. I mean, this is the whole thing. I'm skipping the whole proof. But the point is, it always has this form, this order to it. Any questions? Does that make sense? Okay, we're gonna assume it makes sense. The point is, I mean, like if you look at any of our direct proofs we've done in this class, you'll see, if you go back, you'll see they all look like this. Good. So